Hello, we are Team 29. Meet Bob, a robotic octopus inspired by the octopus Squid. Efficiency through cheap design is about building something that works well using simple, affordable parts. In neuro-robot design, this means creating robots that can do complex tasks without needing expensive or complicated materials. It's like nature, where animals use basic systems to survive and adapt effectively. His body is built with a Lego Spike Prime base for easy customization. He has 3D printed tentacles for an octopus-like appearance and glow-in-the-dark stars to simulate bioluminescent effects. He also has a distance sensor that detects obstacles for smooth navigation and a color sensor that acts as his eyes and identifies predators and prey. He also has wheels, which enable smooth movement like an octopus. To replicate an ocean environment, we used a black tablecloth and paper waves, and for obstacles we used coral and rock. We also had clay predators and prey. Sensory motor integration enables organisms to react to stimuli by linking sensory input to motor output, essential for survival. The lecture highlighted how animals navigate and respond to their environment using sensory systems. Bob uses a distance sensor to detect obstacles, performing smooth turns to avoid them, akin to how an octopus navigates underwater. Bob also reacts to predators, yellow and white Lego bricks, by moving away, simulating fear, and approaching prey, red and green Lego bricks, mimicking hunting behavior. Octopuses use tactile and visual cues to navigate, evade predators, and capture prey. Bob mirrors these behaviors by adapting movements based on sensory input, responding to threats and food opportunities similarly to a real octopus.
In this demonstration, Bob showcases complex adaptive behaviors through a series of interactions that cover principles of adaptive learning and behavioral trade-offs. First, Bob moves towards a prey. He stimulates eating behavior, receiving positive rewards for this interaction. These rewards trigger an exploitation of behavior. Bob becomes invigorated and moves forward towards the area where he initially found the prey. Bob is programmed to increase his encounter time with the prey with each encounter, showcasing reinforcement learning. After this interaction, Bob returns exploring his environment. Suddenly, he encounters a predator. Bob immediately responds with erratic movement, moving with quick. This offensive behavior gets reinforced through punishment. Each time Bob encounters a predator, he learns to move away faster and more decisively. The predator interaction leaves Bob stressed. He begins to explore cautiously, demonstrating a withdrawn state. Even when the prey is directly in front of him, Bob does not interact. This showcases how stress can completely inhibit his normal behaviors. He is too overwhelmed to engage with potential food sources. Bob's behavior illustrates the fundamental principles of adaptive learning. Let's exploit the area where he found the prey and increases interaction time by reinforcing positive actions through rewards. Punishment modifies his defensive response, and stress can temporarily suspend his typical exploratory and feeding behaviors. He also showcases behavioral trade-offs where, depending on his hunger and stress levels, the probability of exploring and exploiting is determined, as well as whether he enters a withdrawn or invigorated state. This demonstration reveals how Bob, like many organisms, dynamically adjusts his behavior based on environmental interactions, balancing exploration, exploitation, and survival strategies.
Conclusion. Bob's behaviors demonstrate the integration of embodiment, adaptive responses, and trade-offs. From obstacle avoidance to predator-prey dynamics and reinforcement learning, he showcases the principles of neurorobotics in action. Bob's adaptive behavior ensures he can navigate his environment, avoid predators, find food, and learn from his experiences to improve his survival strategies.